What's really on the far side of the moon? A journey beyond the visible. Introduction. A hidden world. For as long as humans have gazed upward, the moon has been our constant companion. It rises each evening, waxes and wanes through its phases, and pulls at our oceans with invisible threads of gravity. We've written poems about it, planned our calendars by it, and dreamed of walking on its surface. Yet despite this intimate relationship spanning millennia, there's something profoundly strange about our celestial neighbour. We have never, not once in all of human history, seen its other face from Earth, the far side of the moon. Some call it the dark side, though that name misleads us. This hidden hemisphere has sparked imaginations for generations. Before we had spacecraft, people wondered what secrets it held. Ancient alien civilizations, vast caverns leading to the moon's interior, a landscape you frozen in eternal night. The truth, as we've discovered, is somehow even more fascinating than fiction. The far side isn't dark at all, but it is dramatically different from the side we know. It tells a story written in craters and stone, a story about violence, volcanism, and the chaotic early days of our solar system. Today, we're going to explore what's really on the far side of the moon. We'll examine its scarred landscape, understand why it differs so dramatically from the near side, discover what recent missions have found there, and learn why this remote region may hold the key to humanity's future in space. This is the story of a world hidden in plain sight, separated from us not by distance but by the simple mechanics of celestial motion. Part 1. The Eternal Dance. Before we can understand what's on the far side, we need to grasp why there even is a far side that we can never see. The answer lies in an elegant cosmic waltz that has been playing out for billions of years. The moon doesn't simply hang motionless in space, it performs two fundamental movements simultaneously. First, it orbits Earth, tracing an elliptical path that brings it sometimes closer, sometimes farther from our planet. This journey takes approximately 27.3 days to complete. Second, like Earth itself, the moon rotates on its axis, spinning like a top as it travels through space. Here's where things get interesting. The moon's rotation period, the time it takes to spin once on its axis, is exactly the same as its orbital period, the time it takes to circle Earth. This perfect synchronization means that as the moon travels around us, it rotates just enough to keep the same hemisphere perpetually pointed toward Earth. From our perspective, the moon appears locked in place, showing us only one familiar face covered with its distinctive dark maria and bright highlands. This phenomenon has a name, tidal locking, also called synchronous rotation, and it's not an accident or coincidence. It's the inevitable result of gravitational forces acting over immense spans of time. Part 2. How gravity shaped the moon's spin. Billions of years ago, when the moon was young, it didn't rotate so sedately. Current theories suggest it spun much faster, perhaps completing a rotation in just a few hours. But Earth's gravity had other plans. Gravity doesn't pull uniformly on every part of the moon. The side closer to Earth experiences slightly stronger gravitational attraction than the far side. This difference creates what we call tidal forces, the same forces responsible for the rhythmic rise and fall of Earth's oceans. These forces cause the young moon to bulge slightly, creating an elongation pointing toward and away from Earth. As the moon spun rapidly, this bulge tried to rotate out of alignment with Earth, but gravity fought back, pulling the bulge back toward the Earth-Moon line. This created friction inside the moon, heating its interior and, crucially, slowing its rotation. Over millions and millions of years, the moon's spin gradually decreased until it reached a stable state where one rotation exactly matched one orbit. Once tidal locking was achieved, the system became remarkably stable. If some cosmic impact or gravitational perturbation tried to change the moon's rotation rate, Earth's gravity would quickly pull it back into synchronization. The moon is now locked in this configuration, and it will remain so for the foreseeable future. In fact, the process continues in reverse. The moon's gravity is gradually slowing Earth's rotation, lengthening our days by about 1.7 milliseconds per century. Hey, tidal locking isn't unique to our moon. It's a common outcome when a small body orbits close to a much larger one. Many of Jupiter's moons, including the volcanic Io and ice-covered Europa, show the same face to their parent planet. Saturn's moon, Enceladus, with its geysers of ice shooting into space, is tidally locked as well. Throughout the solar system, gravity choreographs these eternal dances. Make sure to subscribe and watch Part 2.